Hello, I'm Phil Rogofsky, founder and executive director of the Maryland STEM Festival. Today we have a very special program with one of our biggest partners, NASA. We have a discussion of NASA's use of lasers for communications. I'll bet many of you didn't think of lasers as a means of communicating, but NASA and other people have figured it out, and we're going to be hearing about a project NASA has working on it. So first I'm going to introduce Jimmy Avicino, who has organized this presentation, and he'll be turning it over to the principal investigator. So Jimmy, please take it away.
Hey folks, so my name is Jimmy. I'm an educator and intern coordinator over here at Goddard Space Flight Center. We're based out of Greenbelt, Maryland. In case you weren't aware, there was a NASA center maybe in your very backyard. I want to introduce, like Phil mentioned, Dave Israel. So in addition to being the chief architect for the Exploration and Space Communications Projects Division here at Goddard, Dave is also the principal investigator for the Laser Communications Relay Demonstration, LCRD, which you're going to hear a few more times this afternoon. But without further ado, Dave, I'll hand it over to you, and I'll just be here to jump in and ask some questions on the side here.
Okay. So hi, everybody. Yeah, I'm Dave. That's the way too big picture of my face on the cover there. So yes, I have been working for Goddard actually now 32 years. And straight out of college, I was interested in communications. I actually was kind of interested in signals from trying to wire together a home studio to play music with, and you know, the whole rock star thing didn't work out. So I went with NASA and been in the space communications business now for over 30 years. So what we're going to talk about today is this project that is scheduled to launch within weeks, which is laser communications relay demonstration. And so I guess at least on my screen, my face is covering up part of the slide. I don't know if that's an issue for everybody, but so you may have heard that there's there it is, the Artemis program. That is the name of the new program that we have to go back to the moon. This time it'll be the first woman on the moon and the first person of color to go to the moon. So when we went to the moon before, then we sent all of that data back using radio, RF signals, radio frequency signals, and that's how we got the data back. And you've all, I hope, seen those live TV pictures that came back and what the quality of those pictures were. So when we go back next time, there's going to be multiple high definition video streams coming back. So laser communications is our key way to get that data rate up in order to do that. So go on to the next slide, please. Has it changed for anybody else? Jimmy? Oh, there we go. All right, so there is the artist's concept of our LCRD mission. So LCRD, the Laser Communications Relay Demonstration, is not the whole satellite. We are actually a payload on board the STP-SAT-6 spacecraft. So the whole satellite that you see there is the STP-SAT-6, but you see that there's two the two optical terminals there on the bottom, shooting out those laser beams. Actually, those lasers are in infrared, so we make them all red for our pictures because it makes it look much cooler. But in real life, they are not visible. They're infrared signals, and so we have those two optical terminals, and that's what we'll be talking about. Is this mission that will have these two optical terminals and what we're going to do with them. So go on to the next slide. Okay, so the benefits of laser communication. So for anybody that has Fios in your house, or you've at least seen the commercials, so Fios is actually a fiber optical system. So that is using laser and laser light in order to communicate. And the benefit of using lasers is it really comes down to the physics of it. Those higher frequencies and shorter wavelengths mean that you can modulate the signal with more data, so it can carry more data. And also the other benefit that you have is that if you've used a flashlight and pointed it at the wall, or then you used a laser pointer, and you see how the laser pointer, the dot on is much is stronger when you see it on the wall, and it's also focused in a more narrow spot. So the reason why it's stronger is because all the power is focused in that narrow beam, and how that translates to communications needs is that when you send a signal from space and the signal maybe spreads out, then any of that signal power that gets to the Earth that goes and lands anywhere on Earth other than the antenna that you're talking to is really wasted power. And so when you have a narrower beam, then what that does is that focuses more of your power on the target where you're trying to send your data. So the end result is that you can get a much higher data rate, 10 to 100 times, maybe even more than what we do with the RF signals. And then we can also use telescopes that are much smaller than the size of the antennas that we use for RF communication. So we have a term that we use, SWAP, which is size, weight, and power, and that's very important to spacecraft missions because the size, weight, and power is really just a measure of how much of the spacecraft's resources your particular part of the spacecraft is taking up. And unless something is specifically a communications satellite, the purpose of the spacecraft is not communication. So the lower SWAP that the comm system takes up, then that means that there's more size, weight, and power available for the science instruments or multiple instruments or whatever that mission is trying to do. So as we move forward, then the idea is that we'll have optical signals will start to replace those high data rate signals that we have, but there'll still be some RF for other communications needs. Okay, so we're scheduled to launch by the end of this year. The end of November is our current launch date, and so it'll be launching out of Florida, and it'll be the first our first NASA mission with 2 optical terminals on it. We had a mission called the Lunar Laser Communications Demonstration that went to the moon in 2013. That mission, it worked very well, and we sent 622 megabits per second from the moon. But it was on the LCRD spacecraft, which by design crashed into the moon to stir up some dust and measure the dust. But that crash was the end of our optical communication system that we could do experiments with. So LCRD will be in a geosynchronous orbit, and we'll have it there for at least 2 years to do our experiments. Okay, so in this animation, you can see that we have 2 ground stations. One is in Hawaii, and one is in California. And on board the system, we have those 2 optical terminals, which the optical terminal has essentially telescopes. Those telescopes are connected to modems, so those do the transmission and reception. The modems are the things that switch between data bits and photons and laser signals, and then there's a controller that helps to point the telescope. So that's an optical terminal, but in between those optical terminals, we have a data switch. And so what happens is we can have one terminal has a link with one ground station. So you see that the link is with Hawaii. The Hawaii signal will come up, be received on board the LCRD payload. The payload will then take those bits that come out of the receiver, send it to the switch. The switch will send the data over to the other optical terminal, and we see here that it's getting sent to California. Now these ground stations are also set up with simulation equipment, so we can send different type of data to look like different types of spacecraft data, and to do various experiments with it. One thing to notice in this picture, you see the clouds there, above the continent and below the spacecraft. So the biggest issue that laser communications has is that unlike RF signals, where we most of the time can just increase our radio transmitter power and still communicate even on cloudy days, laser communications, once the cloud is thick enough, then our laser won't go through it, and we get outages. So a key part of our experiment is trying to figure out how to work around the clouds and plan for that. Let's go to the next slide, please. So once you get above the clouds, then everything that we learn about communicating by laser and getting through the Earth's atmosphere and the Earth's weather then translates all the way to planetary laser comm. So here you see using optical comm to get data from Mars and back to Earth. And so we'll be doing a lot of our experiments will apply to the future of laser comm well beyond our geo orbit. So there are other constraints that apply when you go even farther from Earth. The most interesting one is a thing called we call point ahead, and as you can see in this picture. So when this spacecraft is communicating back to Earth, you see how it only goes to a small dot on the Earth. So the problem is that when the spacecraft is far enough from Earth and the laser travels at the speed of light. So if you're 20 light minutes away from Earth and you turn on your laser to communicate back to Earth, then you actually have to aim for where the Earth is going to be 20 minutes from now, not not where you might have received a signal from Earth, right? So in that 20 minutes, the relative location of the Earth and the planet and the spacecraft will have moved, and also the Earth would have rotated some. So all that has to be calculated, and you have to point ahead and send your laser in that direction. So the most accurate analogy is you think of like the long pass in a football game where the quarterback has to throw the ball to where the receiver will be when they're running full speed, as opposed to where they are when they see them. So that's the point ahead problem. So go ahead to the next one. Okay, so there's a great picture of our STP-SAT-6 spacecraft, and you see LCRDs there up at the top. That it's a star tracker, and then you see the two optical modules. And we had multiple partners on this mission with us. You see MIT Lincoln Laboratory are really the ones that were the leads for all of this technology originally, and they built the LCRD payload, but that technology has been transferred to industry and to NASA. MIT Lincoln Laboratory is still a contributor and one of the co-investigators on the mission. Northrop Grumman is the provider of who built the spacecraft, STP-SAT-6. Space Force is who's responsible for the STP, is the Space Test Program. United Launch Alliance is who's giving us a ride to space, and JPL are also a co-investigator with us and are the operators, and it's their ground station in California. Okay, so this is this really great animation. So there you can see all of the flight hardware is on one side of that panel, and then there you see the telescopes themselves. The artist did a cool job with all the seeing the Earth in the reflection. what you'll see in this animation, I think it keeps going. I thought one of these animations it shows the lasers and the space station shows up. Maybe not. It might be in a later one. So yeah, let it play again. I'll take. So you see on the panel, you see that's where the modems and the switches and all the electronics is on one side, and then just on the other side, exposed outside, so to speak, are the optical modules, and that's what's pointed down towards Earth. Of course, when you see the pictures of the integrated payload, then there's thermal blankets over the electronics and things. So so even though the optical modules are exposed, then in reality, all the hardware isn't just sort of hanging out there exposed as it is in this picture. So go ahead to the next slide. Okay, so we have our two ground stations. So both locations were chosen because their locations are at high elevations that have minimal cloud coverage. So it's not perfect, but there's fewer clouds there at other places, and then they're also separated far enough that their weather is relatively uncorrelated, meaning that just because it's cloudy at one place, then that doesn't mean it's cloudy or not cloudy at the other place. So you wouldn't want to have your two ground stations so closely located such that if it's cloudy at one place and it's cloudy at the other place, then you don't get that diversity by having the multiple ground stations. So what you see in this picture, so that ball that's actually the radome that covers, and inside of that is a telescope. Let's go to the next slide. Okay, so here's this is the mission and planned missions in our optical comm or laser comm activity. I should you probably noticed that I use the term laser comm and optical comm interchangeably, and people have different opinions about which term is the right term to use, and both of them we use both of them. Some people argument against optical comm is because the light that we use is not visible light. They think that when people think optical, that they interpret that as something that they can see, right? So that's where the laser comm gets used. Sometimes we just choose which term to use because whatever makes the acronym better. So anyway, so there's LLCD, which I said flew to the moon in 2013. LCRD, which is soon to launch next year or soon thereafter. We have T-Bird, which is the terabyte infrared delivery. That's actually going to demonstrate 100 to 200 gigabits per second from low Earth orbit straight down to a ground station. So that's 100 to 200 times higher data rate than what we're doing with LCRD. So that's a huge dump of data from a small satellite. The Illuma-T project is a terminal that is going to fly on the International Space Station, and it's capable of communicating through LCRD. So once Illuma-T is flying, then we'll be able to do demonstrations where instead of us pointing both of our telescopes just to the two ground stations, we'll be able to take one of the telescopes and we'll track the space station when it's flying and communicate to the Illuma-T terminal, and then we'll relay the data to and from Earth from LCRD. So we'll do demonstrations with the space station, and then we're working towards then, after an experiment period, to essentially turn it over to the space station to use that as another connection for them to send data to and from the astronauts and the experiments on the space station. There is another mission called DSOC, which is a deep space optical communications experiment or system that is flying on the Psyche mission, going to the Psyche asteroid, I think it is, and that is where it's going farther out, so that all that point ahead business I was talking about all has to be in place for that. Plus, in order to they had to focus on getting the size, weight, and power down in order to go on a deep space mission where the swap is even more critical for those types of missions. And then on the Orion 2 mission, it's scheduled for 2023. So that is the first mission back to the moon with astronauts on board. This is not the one where they will land on the moon, but it's the first time that astronauts will go farther than low Earth orbit, and they'll go and orbit around the moon and come back. So on that mission, there will be an optical communication system that will be not just demonstrating the optical technology, but that'll be the path that we should all be able to be home and watch streaming HD video of the astronauts in the moon as they get there. So that's the O2O system. So all of these systems, except for DSOC, are managed out of the NASA Goddard Space Flight Center. DSOC is out of the Jet Propulsion Lab, JPL. Okay, so here's the cool Illumity video. So there you see that the optical terminal has to be installed externally on the space station, and then this is essentially the same thing that we saw working between the two ground stations, except now the space station will be in orbit, and the one telescope that is tracking the space station will have to be doing more motion as it tracks the space station when it moves in orbit. So because LCRD is in that geosynchronous orbit location where it's parked over the same longitude of the Earth, 22,000 miles above. So when the space station goes in its orbit, then it really flies at a much lower altitude, and so it will be moving underneath of LCRD, and the one telescope will track it as it crosses around the Earth, and then the data will be switched to the other optical terminal, which will then send the data down to Hawaii, or from Hawaii back up to LCRD and then to the space station. So of course the data doesn't start and stop in Hawaii. We'll have all the connections to get it to Houston and wherever the space station program wants the data to go to. Okay, so with NASA's plans, so of course you've heard the discussions that we're going back to the moon, but the moon is not our the final destination. We want to explore Mars with humans, and then there's also lots of science objectives, Venus and Europa and plenty of other places in the solar system. So we've been working on something for a while that we call the solar system internet, and the part around the moon now that we call LunaNet is something that now that we're really focusing on these days, to give communications and navigation infrastructure for all the humans and systems that are planning to go to the moon, and give type of experience for those on the moon, similar to what we have with our cell phones here on Earth, where you can get network connectivity and you can get the GPS, find out where you are, find out what time it is, and also exchange data. So that's the LunaNet project, and certainly laser communications would be a key way to get those high-speed signals, not just to and from the moon, but perhaps to and from the surface of the moon to the relays. To the next slide. Okay, so LCRD, when it launches, it'll be on NASA TV, and there's plenty of links for you to find to launch it. I'll warn you that the launch time is scheduled for 4:04 a.m. So, but if you're really dedicated, then you can get up early in the morning or stay up all night and watch it. So here's the whole bunch of links. There's now that we're getting in the home stretch to the launch, there's a bunch of stories that are getting out on the like press releases and news stories and other articles and podcasts and videos are coming out. It feels like daily these days. There's multiple activities that you see for all age groups, educational activities, or even just fun activities with a little education thrown in, is all available through these links. And I think that's my last slide, Jimmy, right?
Yep. So I actually wanted to plug on here. We'll be able to share these links out to y'all. We have some activities that are aimed for teachers and parents that kind of go into the math, the engineering, the technology behind here through these links. So if you're a teacher and parent, we have activities for elementary school learners all the way up through middle school and high school, getting into some of the math and applying some of these concepts to your students. So check those out if those are interested. We'd love to hear your feedback along the way. And there are some extra facts about the laser communications portfolio that NASA's put together on here as well. So you can, again, dig into that in more detail and review some of the concepts that we've talked about here today. As or before any questions come in from the audience, Phil, which we're ready for at any point. Dave, can you kind of talk, first of all, you mentioned deep space back here for Gateway and the Psyche mission. What is the definition of deep space?
So the definition that we use is that there's this invisible sphere that is 2 million kilometers around with the Earth in the center of it, and the 2 million kilometer mark, it makes it farther than the moon and farther than the Earth Sun L1 and L2 Lagrange points, which some folks might probably look that up. But it's but those are kind of like the areas of interest in this sometimes referred to as the near Earth region. So that's the definition that we use for deep space. Sometimes you'll hear deep space as sometimes it gets used in other contexts as like when the astronauts go beyond the space station, then people will say like going to the moon is deep space, and it's kind of a relative term. But for what we do, we consider that 2 million kilometer mark like the deep space part. So from the speed of light distance, the moon is only like 2.5 seconds away. And when you getting to the planets, then that's where the delays are measured in minutes. And now Voyager is like, I think it was over 19 hours away last that. So.
Awesome. And can you, so you talked about how the two different telescopes, one can be transmitting, one can be receiving independently. What is preventing, the incoming and the outcoming waves from annihilating or interfering with each other? Is there some fancy engineering behind that, or how do those two interact?
Yeah. So both of them are transmitting and receiving at the same time. So it's like two independent bidirectional links. So they both they transmit at a different wavelength or frequency than they receive. And then because of the separation and the beams being so narrow that they won't interfere with each other as one is talking to one ground station, one's talking to the other. We have talked about and we'll probably do an experiment. Just it won't break anything, but it will just see from an interference point of view of just like putting both of them on the same ground station and doing kind of maybe some interference effects or something. But now there may be some momentary thing if when the space station is flying at just the right time. If the space station flies over the ground station from the line of sight of LCRD, then there'd be a point where it would be in the same beam, but that would probably be for a second or for an incredibly short period of time because the beam is so small and everything's moving so quickly.
You mentioned the word experiment there. My understanding is that the first couple of years of LCRD are going to be dedicated to kind of feeling out how the beam is affected by the atmosphere and what the impacts and sort of what the upper and lower bounds are. Can you talk more about what, first of all, am I correct with that? And second of all, what is the purpose behind that? How, what are we going to learn just by watching how the beams move through our own atmosphere?
Yeah, so we've been communicating with the radio waves for 60 years, now from space, and so there's a lot of what we do when we design in our systems is just sort of based on experience. Like because of weather effects, then you add this much extra power to your link, and we know it will be okay, and we know what to expect, and we've learned it from experience. There was theory going into it, and then we learned from experience. So for optical communications links, we have models, but we have very limited experience of knowing exactly what the performance effects are going to be from the atmosphere, and knowing when the clouds are so bad that we can't communicate anymore. So us really getting a lot of experience to refine those models and to better be able to predict it. The thing is, because we have to switch from one ground station to another ground station once it gets too cloudy, then the better that we can predict when we're going to have to switch, when the weather is going to be bad, and the more accurately we can predict that, and the more in advance we can predict that, then it will allow us to come up with concepts that will allow us to minimize the amount of data loss that might happen, because we can plan better when we have to switch the link from one ground station to another. So that's an important aspect. The other types of experiments that we're going to do will be things like demonstrating there might be a particular satellite mission that is thinking about using laser communications, and we can configure the system with their type of data, and just sort of demonstrate for them so they could sort of experience if they were flying. This is how it would work for them. And then there's also other types of experiments, like if there's somebody that's trying to build a future laser communications terminal, we can work to test and demonstrate with them. Actually, it did come up recently that and I thought it was a great idea, and this is the right audience to bring it up, to come up with. We have a guest experimenter program. And the guest experimenters, I'd actually be very excited to work with a school or an organization to help define some kind of experiment that the students or the groups come up with, and we could design the experiment together, run the experiment with the system, come up with some results. So it's those 2 years are really for us to do NASA experiments, but also intentionally have time and have a whole guest experimenter program to work with industry and universities and others that might be interested.
And this is not an abstract, generic offer. This is an actual program that during the first 2 years, you are soliciting proposals. You would love to people say, "Hey, we want to do this. We want it to run this and this away. Can you all set this up?"
And that's right. It's a whole experimenter program on the LCRD website. There's an introduction to for experimenters document that talks about the sorts of things that you can do, and we have the whole infrastructure in place about. How we evaluate experiments and do all the planning and work out how we're going to schedule them and what we're going to do.
I'll drop that link once I confirm that I have the right link here. Yes, I'll drop that link in the chat for anyone interested. Actually, I think I just have the private chat, but maybe Phil can help me get that link over to the forward-facing part. Or we can share it afterwards. Are there some? Have there been some experiments accepted for that experimenters program? Are we allowed to discuss that or talk about some examples of the kinds of things people are proposing?
Sure. So besides the experiments I mentioned already, there's we're going to do an experiment to demonstrate the networking through the laser communications link. So that's where like I talked about LunaNet, and there's this whole other topic I'd be happy to talk about one day called delay disruption tolerant networking, which is sort of how the internet protocol that we are looking to build the solar system internet upon. So we'll be demonstrating that through the link. We have had some discussions with people that are thinking that they have a terminal that might be capable of being for future users that maybe we would test through it. Let's say there's one university that's interested in doing some sort of like machine learning on trying to interpret the bits. So yeah, we've been getting quite a few. I expect now that the press releases are going out, then there'll be even more. And I think there's some people that heard about the mission a while ago that are holding back until they see us actually on orbit, and then I expect to hear from them then.
Very cool. I wanted to jump back for a second to this slide here when you're talking about Artemis mission. And at some point, I was hearing about the specific landing sites we were considering. Is that still destined for the South Pole? And can you talk about why that particular site was picked and why that's important?
Yeah. So yeah, the South Pole is still what's being targeted. The thing that makes the South Pole really interesting is that there's parts by the South Pole where it has been determined that there is that there's ice, that there's frozen water there. So if there's water available, then I mean there's the possibility of maybe life, but also when there's frozen water, then that makes it the natural resource in order to sustain humans and maybe convert to there's ideas that if you once you escape the Earth's gravity, if you could create basically rocket fuel out of resources that you find on the moon, then it makes it a good spot to then launch to go farther, for example. So so those are and those are the ones. So when it comes to the science part of the moon, back in the amateur category. So those are my best answers for that one. Besides going to the South Pole of the moon with the humans, another near-term goal is to send science experiments to the far side of the moon. And one thing that's especially been exciting scientists for a long time, since the birth of radio astronomy, is to have a radio astronomy telescope on the far side of the moon, because you have the whole moon blocking all of the noise coming from the Earth, right? So you'll be able to hear what's coming from the universe so much better, because all of the noise from the Earth will be blocked out. So the thing is that the experiments on the far side of the moon are going to have to communicate. So we're going to have this challenge of how do you communicate with the experiments on the far side of the moon without messing up the radio free zone, the quiet zone. And that's another case where the laser communications could be the key to that, because then we would just be, if there's an infrared detector, we might interfere with that, but all the radio telescopes won't be interfered with the laser signals.
And so in addition to because it's a much finer beam, it's a totally different wavelength. It won't be nearly as noisy and causing interference to other missions. That's nice for, let's say, a dark side of the moon observatory. I think that also has security ramifications, because it's a lot harder to intercept a fine beam that is tens of meters or tens of kilometers, rather than the radially just going most everywhere. Can you talk about that difference a little bit?
Yeah. So the narrow beam itself does have so it kind of helps you with interference. So when you're receiving a signal and then interference, which is by accident, or if it really is like a security issue on purpose, then if your beam of where you're listening to is much more narrow, then it's much harder for somebody to interfere with your signal. And in the same way, for those, and this is not so much fortunately with our NASA's department, but for those that are concerned about other people intercepting signals, then with the radio signal, with the wide beam signal, then somebody could be far away and still be able to eavesdrop, so to speak. With the narrow laser signal, then somebody would have to be close enough you'd be able to see them. Right? They have to be nearby. Right?
Very cool. And then you talked about size, weight, and power, and the optical, being one of the big benefits of optical terminals. You can fit more modules in there, or they can fly on smaller rockets, or they take less fuel and less energy, or require resources. That's, I think, a great term. Can you talk again about the bandwidth? Talk about LCD as the bandwidth. I think you said 620 megabits per second. That was in 2013. What is LCRD slated to be able to handle?
Yeah, so from the moon it was 622 megabits per second. So with LCRD, we're not making a big leap in data rate. So we're at essentially twice that data rate, 1.24 gigabits per second, and really our limitation was we because our experiment was focused more on like I mentioned, the atmospheric effects and some of these ops concepts and things. Then we decided not to do a new modem development as part of the project, the cost of the project. So we took modems that were available, design that was available at the time, and this is it's been a long road. We turned in the proposal in June of 2011, right? So this proposal was accepted in August 2011 is when I got the letter that it was selected, and there's been various things that have kind of led to it being 10 years later, and we're getting ready to launch. So the modems that are on the Illumity terminal and the new missions are not the same design. Like the technology has improved since the modems that we have on LCRD, but we're still demonstrating. It's still not hampering our demonstrations. But the data rates, when we talk about future relays and data rates, then it'll be multiples of gigabits or 10 gigabits per second, and at a higher data rate than LCRD.
And that's because it's with the higher wavelengths, there are more oscillations per meter of light than in the longer, slower radio wavelengths. It's all moving through space at the same speed, right? It's just that we can pack more information in there, right?
That's right. That's right. And even at the same wavelength, we're not at the maximum capacity at the 1 gigabit per second that you have. So we could stay at the same wavelength that we're at and do higher data rates. It's just that the limitations with the modem technology was more about like the rate, the speed of the electronics at the time, and the clocks and things that are available at the time, and integrated circuits and things. If you think about how much things have changed in the last 10 years. Right?
So I on that front, you mentioned you submitted this proposal in 2011. My final question is, I assume you're going to be very excited at the end of this year to have this launch. What else? What is there a particular aspect that you're most, that you get really jazzed about with this program? Like what's the highlight going to be for you, or what are you most excited to see or to be able to point to?
Well, certainly when it's finally flying and it's working, that's going to be exciting. I guess the thing, like somebody asked me once, like about the success or how I know it's successful, and really for me it'll be at some point down the road when there's some future operational system or commercial system or something that is using information or technology that we learned from this mission. That's the part that I'm excited to see. That like what gets, what does this lead to?
Yeah. So, what is this paving the way for? What is this the next?
Exactly. I mean that's what we're doing it for, at the moment of launch, I think I'll just be thinking of and thankful for all the people over all the years that have worked on it, and we delivered the payload in January of 2020, and it got fully integrated onto the spacecraft by that July. And if everybody remembers where we were and what was going on in January to July of 2020, and just the team just did an amazing job under all those circumstances to get that done. So I'm really thankful for the great team that has pulled it together.
Very cool. Phil, I think that brings us just about to the end of our time, unless there are any other questions or comments you wanted to add to the conversation.
No, people are just very excited about this. I'm looking forward to. You said the launch date's November 22nd at 4 a.m.
Yes.
That's my wife's birthday, so I'll see if I can get up and watch it. But this is an exciting project. We're definitely going to follow it, and hopefully we can have you back to talk about how it has been going since the launch. So thank you both for joining us today, Dave and Jimmy. Again, this is an exciting program, very interesting, and we always love hearing from NASA about the great things that are going on over at Goddard Space Flight Center.
Awesome.
Okay.
Thanks so much.
Yeah, thank you.
All right.
Have a good day.